My name is Suresh Rajgopal from Micron. Today, still not on? All right, how's that? Yeah, in the back? Okay, so Chandra Gura, my partner in crime, along with Pierre Labat, we brought this content here to share with you, and I'll just put together or share our abstract here, which talks about why GPUs and with the speeds that they're operating at need to be concerned with trying to access fast SSDs and how best can that be accomplished. So before that, just to set the stage a little bit on why this problem is of essence for us to be looking at. When everybody talks about AI infrastructure, the three things that typically come to mind is memory, networking, and compute, and that is where a lot of the focus is. But it was nice to hear Curtis's talk right before that when he called out the fact that all that AI infrastructure requires data, and that data typically sits on storage. So some of this is fairly well understood. In the last few years, we've seen the need to store data, need to have high capacity storage. But some of the content that Curtis shared in the previous talk, where he talked about how data is being used, and there are use cases that are developing that are significantly changing how that storage is being accessed and the need for that storage. And that's really where some of the content of this material is addressing it. So if you look at training or inference, GPUs are pretty much at the heart of both. And the figure on the left shows sort of a large-scale AI server, and you can see, and kind of covering it back to the content that Curtis walked through, when you're doing ingest, when you're bringing data in, the data is coming in from remote storage, but then the ultimate destination, this is going into the GPU after it's prepared. During training, the data is read as large data sets coming into the GPUs and then written back. You've got checkpointing that's periodically writing the data, the model states, the optimizer states, back into the storage. So there's a significant path of data going from the storage, the SSDs, to the GPU. And then with respect to inference, and Curtis touched on this briefly, the whole idea of KV cache tiering, that's a new use case where storage starts to become far more relevant versus prior to that, where you could pull your entire model in there, use the GPU memory or the CPU memory to provide the KV cache context. Now you're starting to see use cases where storage becomes far more relevant. So what has happened as far as work in this space of trying to get storage to be more accessible to the GPUs? The first part was making sure there's a fast path for the data from the storage of the SSDs to get to the GPU memory. And some of you have seen work in the past in this space with respect to doing peer-to-peer DMA transfers from the SSD to the GPU memory. So it's sometimes called GPU direct storage or GPU direct bypass. So this is a case where the initiation of the transfer is still happening by the CPU, but the data is transferring directly to storage. The second scenario would be where the NVMe control path is also initiated from the GPU to the SSD. So in this case, the idea is that if the data is ultimately needed by the GPU, then why can't it also initiate the IO required and perform that DMA transfer? And that's really where NVMe starts becoming an important consideration in how we make this happen. And I'll hand it over to Chandra, and he'll talk over the rest of the content.
Can you guys hear me? Nope. Higher? Better?
No.
Can you guys hear me now? Nope. Maybe all the way. Okay. How about now? Almost. Yes. I guess that's how this session's going to continue. Is we're almost there trying to solve all the GPU workload cases. So let me introduce myself. I'm Chandragud. I'm working with Suresh, focusing on performance and QoS in the CPU era. And now we have GPU AI workloads, and we are trying to optimize the performance and the challenge of balancing them both. So as Suresh set up the foundation on how GPUs are now trying to do the I/O management, I would like to bring some perspective on the CPU and GPU I/O workloads, how or what they bring to the table. So let's start with something very simple. So when we talk about CPU-driven I/O workloads or GPU-driven I/O workloads, the throughputs per core typically ranged anywhere between about a gigabyte per second on CPUs. A single GPU can today easily saturate a Gen 6 SSD. There are no issues to manage the IOs from a GPU perspective. When we talk about IOPS, CPUs were traditionally designed with small block transfers, data serviceability, and few million IOPS can be serviced by CPUs in general. GPUs have two types of use cases. We understood that the AI workloads keep changing their patterns. Mostly in CPUs, we had the workloads or workflows balanced throughout all the use cases it was trying to address. GPUs provide us two different perspectives. On one perspective, we are trying to build a big train, pack all the data, and send it on a Shinkansen, like as fast as possible. Try to feed the memory. Keep up to the GPUs. In contrast, we have these new disaggregation workloads where we have KV use cases that are coming in. They are trying to exercise the fact that, hey, if we have petabytes of data access availability present, I have these large set of files, but my weights, my parameters, my models go and sit in a very expensive memory. There is an opportunity to do space reduction where small block transfers can also be enabled. And we have heard announcements from last year to this year, the requirements have gone up tremendously. It's almost reaching 100 million IOPS now. From a latency perspective, typically for traditional CPU workloads, we would talk about somewhere in low hundreds of microseconds. And the quality of service for specifically around reads, going around a millisecond. I'm being very optimistic there, but there are much higher latencies observed in the hyperscalers. GPUs, since they can, it's not about how much I/O we can service through a GPU, it's about how quickly can we start servicing, because the IOs will always be there for us. So it's very easy to saturate a device, and we have to start thinking from the sense of multiple SSDs, multiple Q pairs, completely saturated. So command timeout challenges is some of the perspectives that might show up. And as we walk through these slides, we'll give you some perspective. The utilization patterns are pretty continuous with CPU. With GPUs, it's bursty in nature. Ad hoc demand to do KV cache fill, sudden training use cases. You have a very bursty behavior with a batch type of effect that comes in. It's not continuous. It creates a consistency challenge by constantly ensuring that the IOs are fed to drive these high IOP capabilities. So net, I think CPUs, high IOPS, you could have QoS sensitive scenarios, reads and writes like database operations where small reads are very sensitive in presence of large writes. GPUs, training, we heard about it. We're not going to talk about it again and again. But essentially, training and inference with the prefill and decode disaggregation, it creates different types of workloads that we will start looking at it. So let's dive down a little bit. I'll go one step deep in the GPU side just to bring you to some basics, and then we will go back to the NVMe level. So some preface. This is a good article, I think I would point you to, where it kind of summarizes how GPUs operate in general, why it's different than CPUs. So assume every thread here is a single random read operation. GPUs, the multiprocessor on the top left, you could see that is divided into multiple hardware-driven cores. They could be SM cores or CU cores, depending upon the vendors. These cores primary purpose is to drive IOs. And by the way, they do a lot more things, but I'm bringing a very storage relevance here. Apart from compute, their purpose now is to also submit IOs to the device. These threads are then assigned to a block, and multiple blocks are defined as warps. They all get dispatched by these SM cores. And on a typical GPU, there are thousands of threads capability that is present today. The difference here, as we start understanding the GPU architecture, is GPUs can drive with the capability of this high throughput processor, all the warps simultaneously to the device. So it brings a parallelization perspective onto our devices than serialization. And this comes with certain assumptions that all the memory, all the infrastructure around these IOs are already available. And you're bringing this pipelining perspective. But what, in contrast, it does is if you see the light green versus the white boxes versus the dark green boxes, it says that the IOs get submitted very quickly, but there is a lot of time spent waiting for the IOs to complete. Now, during this time, the GPUs can do two things, either continue to wait for the IO or go back to compute. So a lot of intelligence is already baked into the thread assignment, the scheduling infrastructure, that submits these warps smartly, and at the same time, as the IOs complete, the amount of processing post the data availability is very quick. So then it goes back to dispatching the next ones. What we are trying to highlight here is there is a lot of places where the GPUs now have to wait for the device, while in CPU's perspective, because of the context switch capabilities, it was able to do it more efficiently in the past, but it was doing with less set of IOs. With GPUs, the problem is herds of IOs. This is hundreds of thousands of threads that are ready to go get our data. So we wanted to bring this picture as an example to bring the context, right? And there's no context switching. That's another key message here. When you see in GPU, there's no context switching. Context switches within GPU workloads of going back to the compute or any other operation it needs to serve. But from an IO perspective, there's no context switch in GPU IO thread. The life cycle of the thread is end-to-end. So what this drives to? So what we just saw, where all the batch of IOs, as they get submitted together, it's something called as single instruction multiple thread, SIMT type architecture, where when the CUDA programs deploy these simple tasks of, I need these reads, all these simple codes start from a certain PC pointer, and they all try to simultaneously execute. And that's different than CPU. CPU is much more intelligent. It can handle complex threads. It can wait for memory, go back to do other things. But these are the key messages here. So in SIMT, the fact that every random read, if it's trying to access a specific piece on the device, which is independent of other device, and there is no dependency, it creates a perfect use case for the GPUs to leverage. And that's why the peer-to-peer DMA saw this opportunity of every byte on the device can be parallelly be accessible if provided the capability. Now, what this does, it definitely throws a wrench in the GPU code compilers, and the hardware schedulers need to be very smart in understanding the device throughput capabilities, how many IOs are getting dispatched, and if the threads are waiting on the IOs, they have to loop around. And we will start understanding some of these challenges of what happens when a herd of IOs come in. Okay, I'll continue with a similar story of when these IOs now come and hit the NVMe queue pairs. What are the different types of perspectives of what happens through the CPU fashion and what happens on the GPU side? Okay, all right. Okay, all right. So we'll walk through building this table. So we already saw that the capabilities on GPUs are potentially hundreds of thousands of threads. And these threads may hit one device or multiple devices at the same time. On the CPU, one queue is assigned to the CPU. Generally, the CPU focuses on, I have my queues, I have a specific task, and I can dedicate priorities, reads, writes, and I can do weighted round robin. I can critically suspend, waiting for data. I'm waiting on writes. I can get my reads. A lot of good infrastructure is available on the CPU side. But it still does limited queue pair visibility. It depends on only something called hyperthreading, and we'll talk about that. We already heard on GPUs, I don't want to reiterate there, dedicated hardware accelerators pushing these IOs and just waiting for they're doing the whole IO management. So we just saw the SIMT slide previously. This is what that means. On CPU, you could traditionally run 3 different types of code simultaneously, but with the hardware optimized ideas, same type of code, running on the same line of execution, parallelly accessing different memory, this creates an excellent opportunity to fetch as much data as possible. Okay? So GPUs are very efficient in that piece. And that's where more AI workloads will continue to go harvest this concept of where the sharing reduces and where there is more parallelization available, GPUs can start leveraging this piece. Now, the memory access latency, this is where CPU cores do stall. There's a lot of wastage happening. But this is when a herd of IOs comes in. It's already balanced pretty well for the traditional use cases. We are not challenging any of that. But when there is extreme herd of IOs, these use cases never used to exist. Now we have these use cases, and we need to start thinking about the memory access latency when all these threads are trying to access a shared variable. And we'll slowly start getting into the NVMe perspectives here. GPUs, on the other hand, can schedule all these threads because of the extra hardware available. I mean, cost-wise, you can see there is a lot of differences in how much a CPU costs and the GPU costs. But when we start talking about shared memory variables, everyone has the same problem. So we will start looking into memory access latencies. There is a lot of flexibility in thread assignment. So given you have code A, B, and C, CPUs are very smart. They can say, I have this core idling. I can use hyperthreading, go assign that piece of code to that thread. And it's pretty efficient in optimizing the latency per code. On GPUs, this is a little restricted. As of today, in AI world, I'll never say that this is what's happening. Next year, we don't know what changes. So users typically don't get to assign the threads. And the reason I say is all those threads come as a batch, and they're all hardware optimized today. And we are trying to get all the threads which look similar scheduled at the same way. So the batches are smartly assigned, the batches are smartly operated, but user cannot specifically say, oh, go do this one specific one as an ad hoc request today, as of today. And finally, before we jump into the last bullet, one of the other technical terms from NVMe is the MSIX vectors. These are the interrupts that typically get generated when you have some IOs in the queue pairs. Now, if we start thinking about 100,000 threads, MSIXs already get overwhelmed. Too many operations want to access the queue pairs simultaneously. There is a challenge there in general, right? GPUs today, they do polling. They can't rely on interrupts for every single IO. Perhaps there is an opportunity there on understanding how, given based on the hardware implementation and the AI workloads, is there any sort of efficiency? Finally, OS services are complicated. CPUs do a great job here in handling places where memory and other dependent variables are not available at the time of execution. CPUs are still great. GPUs, on the other hand, are very specific, job-oriented, and their thread synchronization is only the availability within the similar type of tasks. So from this table, what we kind of start understanding is GPUs are very good in certain things. CPUs are great in handling system infrastructure. But we can't live without both of them. Most of these AI workloads today are served by both of these. So there is a challenge on NVMe SSDs or NVMe protocol in general, where both CPU and GPU type of workloads have to be optimized by the SSD. And this creates a huge burden and huge perspective. As you saw, I walked through several attributes through many of the topics, that they are designed differently, but they are trying to solve similar AI workloads, yet maintain the traditional databases, maintain the quality of service. So these are good challenges to have. And as we walk through these things, there is another piece. We will continue to look at these threads. And the reason I'm showing this perspective is, typically we are either doing optimization bottoms up or tops down. We're trying to bring a system perspective on what happens on both sides of the fence. So continuing down the thread synchronization, I'll try to share some data we have evaluated so far on when you connect a really fast SSD. This is not a slow SSD. This is a really fast SSD. Yet, how the utilization, or what are the impacts to the GPU utilization, and what we can do there. So on the left here, you can see two types of vendors. You got H200s and you got the MI325X as an example. I show you those hardware accelerator boxes, the SM cores and the CU cores. They all are simultaneously dispatching 2,000 warp capability. There are 132 cores there. So in total, if you just want to see from a submission capability perspective, 270,000 threads are ready to go on one of the GPUs. And on AMD, from an AMD perspective, one of their GPUs is capable of almost 700,000 threads. Now, there is an aspect that now you come into the NVMe infrastructure, where all these IOs now want to get submitted into the queue pairs. Now, is there a demand to submit all 270,000 to a single device? No. Is there a need to service them all together today? No. Because the end device is not capable of handling all this, and it makes it worse on the end device, saying, I have this capability of submitting the IOs, but then what happens next? And that's where we are focusing a little bit more. As part of dispatching these IOs, to the bottom, today you see that every thread has something called as a sync code. Each SM core, when it runs this thread, there is a need to perform sync. And the reason for that is once you are looking at the lower level latency stacks, there is no way that you don't have a shared memory resource. And in QPair, one of the key aspects is, for example, I want to submit all the IOs to a QPair, and I have to update a shared resource, which is the doorbells or the head and tail pointers on our QPairs. They're all trying to simultaneously attack one or two or more. In order to solve this, what happens is the sync code then stalls the warps because let's say I processed 100 of them and I updated the register. What is the resolution at which all these GPUs are submitting, and then they are waiting for that shared resource to say, hey, device, you have all these IOs, go. So there is a thread synchronization effect that happens due to the shared variable lock that from an NVMe protocol perspective, we get it. Today, it stalls, so every thread is then operated serially. And it is okay because the end device bandwidth is not so much. But if you connect multiple SSDs, that is how they're solving it today. You could have multiple SSDs connected to reach the 100 million IOPS, right? But in future, it is possible that this bottleneck can be improved if the end device is much faster than what we have today. So bringing that challenge of synchronization points, which I said, which happens on the submission queue, all these threads are trying to do an atomic memory operation to submit these IOs to one or more QPairs. And when these writes happen on the QPairs, you're trying to access that shared variable. In case of submission, it is the tail doorbell that needs to get updated. The device, on the other hand, as it's processing these IOs and fetching certain amount of IOs, has no context of the burst nature from the top. All it gets to see is saturated buckets of QPairs with thousands of IOs on it. But is the servicing of the IOs uniform? Is there a fairness required? What type of challenges would be there on how many IOs should I fetch from what QPair? Because here all IOs look equal to us. There is no weightage around that piece. So the way the GPUs solve it today is they parallelly write it on multiple QPairs. Okay, that's excellent. And then they can ring the doorbell saying, hey, all these tails are updated, go start working on it. But it creates a cost on the device side now, saying, I got to walk through all these QPairs just to get these IOs. Okay, that's a hardware cost. But as the traditional bandwidth requirements are concerned, they're fine. But are they optimized for future? Now, what impact this does to the top level? So as we are trying to synchronize these threads, there is an impact of scheduling the SM resources. And there is a lot of, not code bloat, but a memory bloat to manage all these IOs from an SM perspective, where the IO submission tenure keeps extending as we start submitting these IOs. And the faster the memory usage or the access or the update is, the faster it gets. But today, it creates a serialization impact on the GPUs where the SM cores are trying to use more L1 cache bandwidth just to manage their QPairs. So it went into a little deep topic, but I'll now slowly start coming back to say there is a cost to submit the IO. If you submit the IO, it needs to be updated quickly. In order to do that, there is a memory cost on the GPU front to manage the IO. And if you have to do this for thousands of IOs, it has a linear effect. So when we close out this particular synchronization piece, one of the key messages here is, as we are looking into connecting the raw device to the GPU, it's not only the bandwidth requirements we should evaluate, we are also looking into the stack latencies on how quickly we can release the burden of IO management on that SM core, so it can go and do some other warp, which could be a compute, which could be a DMA fetch, it could be hundreds of other things. Now, there is no suggestion here that the existing protocol doesn't work. We are just throwing out the challenges here, and we want the committee to start thinking from that perspective that there is a metric, there is a new set of metrics from GPU perspective that we need to continue to evaluate, which is GPU memory sizing, the IO workload management, and the shared variable access times. Okay, so we did touch on another topic. We'll touch on another topic, and then we'll kind of start summarizing. So what is the cost of interrupts versus polling? So there is nothing wrong with interrupts. There's nothing wrong with polling. There is a cost on both sides. Polling is very well suited for the SIMT architecture, and that's why it's pretty obvious. If you're running the same set of code, all pointers are at the same, all code executions run parallelly like a lockstep, there is no need for interrupts. It knows that it's waiting on data at this point. The hardware intelligence says that I have this batch of threads waiting on these set of IOs. Now the impact of the device starts showing up. If the device has high bandwidth potential, but no weightage of understanding that the IO that was sent on warp 0 or warp 256, I might be processing it out of order. There is no method to madness. It's all fair game. I need to maximize bandwidth on the device, but which SM core is waiting? How is the scheduling designed? Is there a fairness involved in the end-to-end system stack? These are the key things or the challenges we would like the commit industry to start thinking about, as how the better the device is aware about these things or devices are, the better we can handle them. So, but at the same time, I did mention that we cannot live without CPUs. So you still have interrupts. So it is possible that the same device is designed for the CPU in mind, with existing cost of setting up the MSIX and the interrupts and the whole hyperscalers or the OEM workloads. At the same time, you have this no polling architecture trying to demand as much bandwidth. It creates an interesting challenge in the hardware cost. And we have to start sensitizing this around about how many completions, how we are completing these, and this has end-to-end impacts across the system. So interrupts do have very expensive cost on synchronizing these threads. But when a batch of IOs which have similar operations to do, perhaps there is an opportunity there, right? And that's why interrupts versus polling is yet another challenge that we need to address in the protocol. All right. With that said, I would try to come back to what this creates as two challenges. One, as GPUs will go faster and faster, there is no limits to the token sizing. We are seeing million contexts already, and it's going much faster. GPUs will start talking to each other. The scalability challenges are immense. We will have thousands of Q pairs, whether it's single device or multiple devices, which may get these IOs. So from an NVMe perspective, that's one of the areas. How will we address Q pair scaling challenges? There are fundamental attributes we did discuss: the doorbells, the MSIX, the head and tail pointers. There is latency cost involved in the top level stack in order to service this. This latency is clearly visible for GPUs. The longer we stall them, the less dollars they make. So we would like to evaluate this path carefully for future. Does it scale? Does the current design scale? We are not opposed to whether it works today or not. It works. We are already seeing the devices being connected both sides. But does it scale for future? So these are the type of questions we are trying to ask. One of the things that we didn't talk about is the transport protocol. So PCIe is getting extremely overwhelmed now. It's getting busy with these. Now think about this. If I have a large train with thousands of users on a single track, it's easy. It's a single transaction going across. I have a traffic full of small cars going into city. That's the impact the small block transfers do to the PCIe now. Every single I/O has to go through PCIe. Is there a better way? Is there a cost? Is there a way we can reduce the cost of this overhead? So as today there is no bottleneck from a simple bandwidth perspective, but as you start looking at these end-to-end latencies, these are the questions we need to ask. Does it scale for that? And the bigger challenge is it's not about the capability to do it. It's everything is now driven in hardware, and the cost of designing these hardware dedicated accelerators or blocks is many, many years. So having these studies early is critical, and understanding them is key. And the last point is not the least, it's perhaps the most important. The devices have to be connected to two different radical ingest engines, I would say, right? There's a CPU and a GPU. While we have to maintain the traditional workloads from these devices, we have the challenge and perspective that both of them have to coexist in the same protocol for the end device to start understanding that it's different. We cannot build custom solutions for one type of workload. AI workloads keep changing. So these workloads will continue to change as we find opportunities with an inference. And the access to data is not once. That premise is already broken. There will be repeated accesses to the data in order to serve an end user. In order to do that, we have to look at the existing infrastructure, which is very key. There needs to be resilience. There needs to be management to manage these devices, the error triage capabilities, and the telemetry. All of this existing infrastructure should still reside while we are servicing these really high, fast bandwidth needs and the IOP needs that are thrown by us. So now I would like to call Suresh to kind of walk us through the call to action and the next steps in the industry.
Okay, so Chandra covered a whole host of challenges for NVMe in being able to manage a new set of I/O traffic coming in from GPUs while still being able to service the CPU side. So fundamentally, that requires, the first phase is with respect to handling NVMe queue arbitration, being able to manage the doorbells, and being able to handle shared variable access while managing polling as well as interrupts. Large queue demands, which NVMe controllers typically can support, but at the expense of cost, also needs to be examined. And lastly, as AI usage scales, you're moving to a phase where you've got multiple GPUs potentially accessing stacks of storage. So the question would be, beyond NVMe, is there a need to improve PCIe efficiency? If the transfers get really small, is the overhead of the payload going to be dwarfed by the amount that the header actually takes? So being able to deal with other opportunities to optimize that would also be another space for us to look at. So certainly a lot of things for us to look at in NVMe as we look at trying to support use cases of beyond just doing DMA transfers between SSDs and GPUs, but being able to service GPU as an I/O initiation engine. Thank you. I think we've got time for questions. Go ahead.
about the NVMe. Are you guys solving this problem with the recording this session? Use the mic, please. Do we have a mic?
The mic isn't working.
Okay.
So,
Repeat.
so my question is very simple, that you have a lot of good ideas with NVMe, and the UEC is another transport, that NVMe and UEC are getting together to solve it under UEC storage technical committee. So are you bringing those NVMe future into either NVMe UEC committee or in NVMe committee to solve these problems? Is my question.
Okay, let me repeat the question. The question was, there's a lot of other work going on trying to bring NVMe on top of UEC, and the question was, are any of these ideas being brought into either the NVMe or UEC consortium, or is this being dealt with separately? And the honest answer is right now we're just painting the possible challenges. So if this potentially could be something that the NVMe committee would want to discuss, is if, depending on what the underlying physical transport protocol is, whether it's PCIe or UEC, how should these challenges be addressed? But that's more for the committee. Stephen.
Great talk. Has Micron looked at security around this at all, or any thoughts there? And when I say security, I mean both in terms of the GPU might be trying to read or write to namespace regions it shouldn't really have access to, but there's also the DMA security side in the sense that now we're going to have these random devices, starting DMAs to places that we might not necessarily want them to DMA to, especially in multi-tenant environments.
Okay, so just to repeat Stephen's question, has there been any work looking into security while accessing these devices, both in the context of being able to have shared namespace access but being secure, or being able to restrict DMA transfer to regions that are perhaps not permitted? So security is certainly a consideration. I don't think it has risen up to the level at which we've started to look at it, but I suspect PCIe and NVMe have plenty of capabilities to be able to manage that. So there's IDE for the transport protocol, there's TDISP, which can be deployed, and then eventually being able to manage through some form of virtualization if you're able to manage shared access to namespaces, but being able to restrict that. But I think a lot of that needs to be done in conjunction with the use cases and which data needs to be protected and what the software stack does above it. So it's still early. We're on the back.
So I understand that there is a scalability issue having individual queues for each of the GPUs, but have you looked at delegating the entire queue to the GPU? And that way you don't have to have interrupt and pulling, you don't have to keep that uniformity with every queue. You can choose which queues you have interrupts on and which ones you have queues. Have you looked at just delegating the whole queue to the GPU?
Yes, there are. So the question was, have we looked at alternate approaches for GPUs to optimize to limiting the number of IOs to maybe single queue pairs and reduce, there's no need to pull, and all sorts of evaluations. Whole queue pair. Okay, so queue pair managed by the GPUs itself. Yes. So the question is, if the queue pair itself is managed by the GPUs, is there any studies being conducted there? Yes, there are. We have done some, based on the limited availability of infrastructure we have today, we have done some sort of basic end-to-end understanding. We layered it with the stack analysis as we showed. This is the first premise. And then we have swept the XY dimension. Some of this gets into IP, which we can talk about, but the challenges that we have brought out here today are some of the outcomes. So the memory tenure of the GPU metrics and the SSD metrics are clearly visible. And there can be more studies done in this path to optimize that fashion. And that's where we would like, there could be more radical ideas, let me put it that way. But the question is, at a certain point of time, there has to be a conversation at NVMe level on prioritizing these challenges, and if the existing solutions can solve them, let's address it that way, or we have an area of opportunity to optimize it. So I'll leave it at that. So, okay. Yeah, so the question was, doorbell stride is a challenge today. So there could be ways to improve it. Now, that's an excellent topic. I mean, this is why we are raising awareness here. It's many parts of the NVMe protocol that has to be discussed and looked at. And I know the audience have already raised security as a topic. You have raised MSIX, doorbells. Everyone has to evaluate all of these from a different perspective. Like, step back, look at the whole stack from both sides, and let's co-innovate in this space. So, okay, question, CJ. So I'll try to summarize. CJ's question is, as we saw the NVMe attributes and multiple challenges with the protocol, one of the key aspects is queue pairs are serial in nature, and perhaps we have to look at more opportunities in that space to start thinking more for future I/O demands. And from his perspective, he would like the industry to collaborate in this space. So, okay, I think we are done. Oh.
Reiterate the first question, which is, and I'll say it a little differently, nothing happens in NVMe until someone brings in a proposal.
Yes.
Agreed. Paul's comment was, nothing happens in NVMe unless somebody brings in a proposal. So certainly, I think that is the first step in taking anything in to create a TPAR. So once we get there, and we're open to collaboration. Thank you.